So this week we're going to be talking about the Sun. I'm going to start off with this, which is just a compilation of data, and we'll go through some of these issues. We already talked about how we know the distance and the fact that it changes over time. The light travel time is basically just how long it takes light to get to us. We've already talked about the angular size in terms of eclipses. Its actual physical radius, since we know its angular size and its distance, we can work out how big it is. It's about 100 times as big as the Earth. We'll come back to the mass very shortly. The composition we know from spectroscopy, and here we've got it by mass, so it's about 75% hydrogen, 25% helium by mass, but because hydrogen is so much less massive, it ends up with a lot more atoms. Its average density is a bit more than water, and its surface temperature is about 6,000 Kelvin. We'll come back to some of these things later. But first, let's just remind ourselves how we know the mass of the Sun. And so we derived this equation that is a version of Kepler's laws using Newton and centripetal force. So if we have the period of a planet's orbit and its distance from the Sun, we can work out how massive it really is. Because the planets, even Jupiter, you can basically neglect the M2, the mass. You get an equation that looks like this. This little symbol here is the symbol for the Sun. And so we can rearrange this so that if we know the period and the distance, we do, the period of the Earth is a year and the distance is 1 AU, plug that in and we come up with a mass of about 2 times 10 to the 30 kilograms. And this is just a summary of the composition, so it's mostly hydrogen, and then you have a little bit of everything else, and we talked about this when we did the formation of the solar system. Okay, so what is the structure of the Sun? Here we've got a cross-section through. So basically the surface is here where it says photosphere. The inside, there's a core in the center, which is where energy is being produced. There's a radiation zone, which is where the energy is transferred from the core outwards via radiation. It travels as photons. Then there's a convection zone, which is where it travels by moving material, just like convection in a pan. Then you have the photosphere, which is essentially the surface. We'll talk about why that has a finite depth. Then you have the atmosphere, which is made of the chromosphere, and then transition zone into this corona, and there is a solar wind that is material flowing off the Sun all the time. And so this is just a summary of that with some dimensions. So here we've got the core is about 15 million Kelvin, and it has a very high density. As we move out, we see that the density drops rapidly. The temperature drops as we move out to the photosphere and even into the lower atmosphere, but as we move out again, it heats up again, and we'll talk a little bit about that. And here you can see what the radius is for these different zones. Okay, so here we're going to start with the interior. So we've got a core where energy is being produced. We've got a radiative zone. So like I said, this is where energy is transported as photons. It doesn't just travel straight because it bounces off of the atoms and nuclei that are in there, but it does move as photons and not by moving material. But in the convective zone, the energy is contained in here in the particles of gas, mostly hydrogen, and so it is the gas that's moving. And we're going to look at how we know this stuff. But one of the questions that is interesting to think about is, in the Sun, it's a big ball of gas. So this is true for the atmosphere of the Sun, for the interior of the Sun, for the atmosphere of the Earth or any other atmosphere, and even oceans. Why doesn't everything just collapse down into a thin layer? And so we're going to look at what happens here. Excuse me. And essentially it's down to the fact that gas has pressure in it. And so what you've got is you've got a downward force of gravity. So here we can consider a section of the Sun as having a particular mass and therefore has a weight due to gravity pushing down. It's a force downwards, and then it's being supported by the pressure of gas below it. But there's also pressure coming from above, so there has to be a balance between the weight down, the pressure down, and the pressure up. And when you have this, that is to say that when it's completely stable and you don't get radial motion, you don't get motion up and down, this is called hydrostatic equilibrium. Like I said, it applies to the atmosphere and it applies to the oceans. And so what you need is that this pressure down here below the slab must be greater than this pressure up here, because this has to be the force on this slab has to equal the weight and the pressure from above. And so you automatically get higher pressure below and lower pressure above. And this should be familiar to you because we know that as we go up in the atmosphere, the pressure gets lower and lower. And even in the ocean, as you go down in the ocean, the pressure gets higher and higher. And it's all from the same cause. So let's actually consider this. So we've got a slab of atmosphere or sun, doesn't really matter which. Here I've got this slab. It's just a nice rectangular slab. It's got a force of gravity, Fg, pulling down on it, which is given by ma, where the acceleration is the force due to gravity, and the mass is given by the density of the slab and its volume. And the volume is, we've got an area A and a thickness delta R. So area A, thickness delta R gives me the volume, and the volume times density gives me the mass, and then gm over r squared is the acceleration due to gravity. And what we have is that there is a net upward force on the slab that is, you've got a pressure P pushing down and a pressure P pushing up, and delta P, the difference between pressure pushing down and pressure pushing up, must equal this gravity force. And so here I've got A delta P, so this is the area times the difference in pressure. That's the net pressure from below, equals that weight, that gravity force. We can rearrange this. I put the delta R on this side. Now I've got the rate of change of pressure with radius, and it's given by the density and gravity, but gravity is also radially dependent. As we take delta R to 0, so we go in infinitesimally small steps, we get really the dP by dr, the rate of change of pressure with depth into the sun, or into the ocean, or into the atmosphere, and so on. Okay, it applies to any pressure-gravity balance. So let's start by assuming that the sun is an ideal gas. This is not bad. It actually does behave mostly like an ideal gas. And so we have that the pressure is equal to the number density of particles in the gas, the Boltzmann constant, and the temperature. This is pretty much the same as PV equals nRT, but the V and the R are now inside this little n and the K. But little n is the number density, which is the same as the mass density divided by the mass. And so we can say that the pressure is rho K T over M. And we can rearrange that to get rho. So now this is M P over KT. And remember that we came up with this equation, which is dP by dr equals rho of r g m over r squared. And so now I'm going to plug in my rho in here. So now I've got dP by dr is dependent on P, and the mass of the particles, and the temperature, and the mass of the star, or the atmosphere, and so on. And then I'm going to rearrange this so that I have pressure on one side and radius on the other. Okay, so that's the equation. I've got the pressure on one side, the radius on the other, and we could also, for simplicity, say that G is, this is basically where F equals gmm over r squared, and F equals m little g. So that just makes it a little easier to manipulate. So now I've got this equation. Remember, m is the mass of the particles, k is the Boltzmann constant, T is the temperature. If I integrate this, I get the natural log of P is given by this equation, which is going from R to R0. There should be an R in there. That's odd. Okay, there should be an R in there. And so now the pressure at some radius r compared to some 0 r for the sun, that would be the center, but for the atmosphere that might be the surface, is given by the exponential of g m over kt r over r squared. So you get an exponential increase as you go down into the sun, or an exponential decrease as you come from the center outwards. And we're not going to go through all the details of this, but basically if you use this equation along with the fact that you're making energy and what's giving you the pressure, you can work out the structure, and that you have a dramatic rise in the temperature and the density as you go from the surface to the center. So here I've got the core. In the core I've got a very high density and a very high temperature. Temperature drops off until you get to the surface, and likewise here the density drops off to essentially 0 at the edge. And that's the first part of the Sun. We'll come back and talk more about what's going on the inside.